Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video series, we're to finish up our series on net ionic equations, specifically oxidation-reduction reactions, which sometimes are called redox. I got a whole bunch of notes on the board that we're going to go over, and then we're going to go into balanced chemical equations, complete ionic equations, so that we can get to our net ionic equations. Now, something about oxidation numbers that you need to know is how to assign them, okay? So we kind of have this priority system where we assign oxygen as a -2, then hydrogen a +1, and then the halogens as a -1. So, for example, let's say I had this compound FeCl3, and I wanted to assign some oxidation numbers to it. No oxygens, no hydrogens, but I do have a halogen as a -1. And if I have 3 chlorines that are -1, that means that the iron would be a +3. Now, oxidation numbers are very similar to charges, okay? Typically, when we do oxidation numbers, though, we typically put the sign first and then the number. Where charges, we typically put the number first, followed by the sign. Now, in ionic compounds, typically charges and oxidation numbers are basically the same thing, okay? But if I was giving you a true definition of what an oxidation number is, it's a way that we kind of like bookkeep our electrons. Okay, let me give you an example of something that is not ionic. Okay, carbon dioxide is not an ionic compound. Okay, so it technically has no charges, but we still want to do this bookkeeping of electrons. So we assign oxygen as -2, and this whole compound's neutral. And if there's 2 -2s, then that must mean that the carbon is a +4. Now, I want to remind you, carbon and oxygen are not charged. This is just a way that we kind of keep track of the electrons. And to maybe make this make a little bit more sense, I'm going to go ahead and show the bonding of carbon dioxide. This is kind of like what it looks like, where the electrons are pushed away from the carbon and towards the oxygen. Okay, so if these electrons are being pushed away from the carbon to the oxygen, it seems like if we were keeping track of the electron, this electron's going away, this electron's going away, this electron's going away, and this electron's going away. And that's why we say carbon's kind of like a +4, but it's not a full charge because these electrons are not being transferred. They're still being shared. So that's kind of like the major difference between a charge and an oxidation number, is that we're kind of just keeping track of where the electrons are going, but they're not fully charged when you're dealing with molecular or covalent compounds. So I hope that helped you with kind of like assigning these oxidation numbers that you're going to see me doing when we do this net ionic equation. And then we need to talk about what exactly is oxidation and reduction, and we're going to go over these notes through our first example. So let me kind of erase the notes on how to assign oxidation numbers and get into our first example, which is going to be zinc with hydrochloric acid. So zinc with hydrochloric acid is going to produce some zinc chloride and hydrogen gas. Okay, now if I'm doing a balanced chemical equation, I believe I have to put a 2 here. Okay. Whenever you see this single displacement reaction, like ding, 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 it's probably going to be an oxidation reduction reaction. Our other 2 net ionic equation problems that we did were precipitation reactions and acid-base reactions. Those were almost always double displacement. And here we have a single displacement reaction, so I think there's going to be an oxidation reduction reaction. Let's go ahead and assign oxidation numbers. Elements by themselves are always neutral. Elements by themselves are always neutral. Now the compounds, we have to assign those oxidation numbers like I told you. No oxygen here, no hydrogen here, but we got the chlorine that's a -1. That makes the zinc a +2. Okay. Over here we do have the hydrogen, so it's a +1, but it also works out that the chlorine's -1. So these are the oxidation numbers. Okay. What's happening in this equation is that zinc is going from 0 to +2. And the only way it can go from 0 to +2 is if it's losing 2 electrons. So the zinc is going from 0 to +2 by giving up 1, 2 electrons. And remember, electrons are negative, so if you take away the negative stuff, you're going to make something that's positive, okay? So when you lose electrons, you have an increase in oxidation number. It went from 0 to positive 2. Well, if the zinc is losing the electrons, there has to be something else that's gaining the electrons. And whatever gains the electrons is going through reduction, and we should see a decrease in oxidation number, because if you're neutral and you start taking in electrons, -1, -2, -3, -4, that's a decrease in oxidation number. And what's decreasing here is the hydrogen. The hydrogen's going from +1 to 0. Okay, so if you have a decrease in oxidation number, that means the hydrogen gains some electrons to go from +1, okay, to go from +1 to 0, and that's because the zinc is giving up those electrons. So that's a brief explanation of kind of like how oxidation reduction works. You're going to have one thing that's losing electrons and another substance taking those electrons in and gaining those electrons. And you can't have one without the other. If you have something that's losing electrons, you have to have something else that's gaining electrons. And if you have something that's gaining electrons, you have to have some other substance that's losing those electrons. Okay. Now, we also have to make this a net ionic equation. So we come back to all the rules that we talked about already with what things we split up and what type of things that we keep together. So let's go ahead and do the hard part, which is deciding if things are split up or kept together. Okay, so we got an element. Okay, so I'm not worried about that. Do you split up a strong acid? Okay, HCl is on my, it's on my list of strong acids. If you forget where the strong acids were, it was just the previous video that I had them placed right over here. Okay, but if you forget that list, okay, you need to go back to that previous video on acid-base reactions to find the list of strong acids and strong bases. But this is a strong acid, so we are going to split it up. And if you notice, I am now using charges because I'm talking about ionic stuff. Okay, so we're talking about ionic compounds now. And that's going to make zinc chloride. And is chloride a soluble ionic compound? Okay, so I look up my solubility rules on chlorides, and I find out that chlorides are soluble except with silver, mercury, and lead. It's with zinc, so it's soluble. So it means we're going to split it up, and it's to split up into a +2 ion and 2 -1 ions. Okay, of course we're going to leave the hydrogen by itself. Okay, and it's still neutral. So our elements are still going to stay neutral. You don't have to put the zeros up there, but I like to put the zeros up there to remind students that elements, okay, in their elemental state by themselves are always neutral. Okay, so the last thing we have to do is just cross out our spectator ions, okay, and then rewrite everything. So zinc as a metal is a solid, okay. This is going to be in solution because it's an ion, so ions will be in solution. The zinc ion is going to be in solution, and then the H2 is going to be a gas, okay? So the things that are neutral up here, okay, I'm just looking at the periodic table and deciding if it's a solid, liquid, or gas. A lot of periodic tables are color-coded that will let you know that. Some instructors make you memorize which things are solid, liquids, and gases. But zinc is black on my periodic table, which tells me that it's a solid. Hydrogen is red on my periodic table, which tells me that this is a gas. Okay, things that are charged are always in solution. Okay, so the elements, you look on the periodic table, the solutions, okay, that are charged, they're always in solution. So I just want to make sure you guys recognize that in this oxidation reduction reaction, you have one thing that's going up in oxidation state, and you have another thing that's going down. Okay, the number one mistake that I find when I'm grading tests is that students want to just give me one of these. They either give me the zinc that's going up, or they give me the hydrogen that's going down, and you can never have that. Okay, if one thing's going up, another one has to be going down, because if one thing is losing the electrons, the other one has to gain them. Okay, let's do one more problem. Let's take a look at iron bromide. So I'm going to write this as a balanced chemical equation, so you don't have to practice that in this particular video. We're going to mix it with 2 aluminums, okay, and that's going to make 3 iron and 2 aluminum bromide. All right. So same thing as before. Let's go ahead and assign oxidation numbers first. Remember, elements are going to be neutral, okay? And then our halogens are going to be -1s. And if I have 2 of them, that makes this iron a +2. If I come over here, -1. If I have 3 of them, that makes the aluminum +3. And here are my oxidation numbers, okay? And when you look at this single displacement reaction again, okay, ding, 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 it's probably oxidation reduction. You better find something that's going up in oxidation number, and you better find something that's going down in oxidation number, okay? If we look at and focus in on the iron, it's going from +2 to 0. That means it's going down. There better be something that's going up. And the aluminum's going from 0 to +3. So I feel pretty confident that this is an oxidation reduction reaction. Now I just need to do the hard part and decide, do these things split up or do they stay together, okay? And the only solubility rule you need to know for this problem is bromides, okay? Bromides are usually soluble unless with silver, mercury, and lead. It's with iron. So it's soluble, it's going to split up. Now when we split this up, we're going to split it up into 3 irons. And there's going to be a total of 6 bromines here. Now they're all charged, okay? So remember, when things are charged, when they're charged, okay, it's a coefficient. The only time that this would be a diatomic, okay, is if bromine was by itself and neutral, okay? It's not neutral, it's charged. Anything that's charged is going to give me a coefficient, okay? We got 2 aluminums. Now, I remember that that's 0, not necessary to put it in. I just do that for instruction. And we're going to get 3 irons that are neutral. And this is going to split up into 2 aluminums and 6 bromines again, all of them that are charged. Okay? So we're going to cross out the spectator ions, which are the bromide ions. And that's going to leave us with 3 irons that are charged. And if it's charged, remember, that means it's in solution, okay? And it's going to bump into 2 aluminums that are neutral. Now, if it's neutral, I look on the periodic table to determine its state of matter, and it's a solid. Same thing over here. I look up the iron. It's neutral. It's a solid. It's black on my periodic table. And 2 aluminums, and these are charged, so it's going to be in solution. So I'm hoping that I see something that's going up in charge and something that's going down in charge, and that lets me know that I probably have a good oxidation reduction reaction, okay? If you found this information helpful, please give it a like, subscribe, and even leave a comment, because that helps the YouTube algorithm get this out to other students that are interested in learning some net ionic equations, specifically oxidation reduction.